Okay, off we go. So last time, here's... no, that's not it. Here's the last thing we talked about, according to my records, and that was this idea of accumulation, and in particular, that boundary circulation is an accumulating quantity. And I'm going to say this is a little bit of a surprise. It's a weird little reality. Let me remind you where all this came from in the first place. The reason we were interested in accumulating quantities is because accumulating quantities behave like physical substances. I mean, in the sense that they can be viewed as distributed over the area, and they just behave that way. And so you might as well treat them that way, which allows us, for example, to talk about their associated density. And as soon as you understand it as having a density, you can compute with an integral. So this is actually a really powerful strategy. Any time you identify an accumulating quantity, any quantity where the whole is the sum of the parts, it's really all you need. Everything follows, and you can compute that quantity with an integral of an associated density. So the fact that boundary circulation accumulates is a huge punchline. And real quick, and I'd love to spend time on this again, but we don't. We're always in a rush. But roughly speaking, the reason why it accumulates is because if you look at what a boundary circulation looks like, let's say on the left side, and what does a boundary circulation look like on the right side, and you compare that to the boundary circulation for the whole, everything matches up. Green plus blue is equal to purple. Everything matches except for this stuff in the middle, but that stuff in the middle is two line integrals over the same edge, but with opposite orientations, and so they cancel in a puff of smoke, and it's like it was never there in the first place. Right? It's this awesome little magic trick. And so boundary circulation is an accumulating quantity, and we're in business. It's an accumulating quantity, so we can write it as an integral. And that's all Green's theorem is, as it turns out. So here is the resulting Green's theorem. We were looking at this quantity defined on areas, namely circulation. Remember, we use this little sigma symbol, lowercase letter sigma. That's a quantity defined on areas, boundary circulation. We noticed that it's an accumulating quantity, so the whole is the sum of the parts. So we can write that down. And again, associated notion of of density. Density ends up being the curl. And so we can write down this theorem, and that gives us Green's theorem. Right here. Oh, hang on, I wanted the color switch. There we go. A boundary circulation can be computed as a double integral of curl. Now, I've skipped over some details there. In particular, I skipped over the business where I computed what the density is. And again, I claim that density, circulation density, how much of this stuff is there per unit area? How much circulation is there per unit size? Thus the term, circulation density. And I claim that it's equal to this formula, which y'all will recognize from Chapter 3 we previously called curl. How do I show that this formula works is what I'm going to call details. And if you want to see those details, it's in the book. If you want me to sit down with you and show you how that argument works, I'm happy to do it. But it's just details. I think it's much more important to understand what it means, why we care about it, how to think about it, the much more important thing. And again, my take, why we care about this formula is because it is a density for the accumulating quantity of circulation. All right, now I'm just going to really quickly mention some notational alternatives. Curl is the most common term for this expression. It is sometimes written as rote. R-O-T, that's short for rotation. And I'll talk about why that is in just a couple seconds. You might even be able to kind of piece it together yourself. A kind of a convenient little shorthand. As it turns out, y'all may recall this little, this little thing right here, the wedge product. We mentioned this long ago, back in chapter 1, when we were talking about cross products and triple products and things like that, and I noted that there was a two-dimensional kind of, it's not an analog exactly, but it parallels. I mean, it has a lot of the same properties in certain ways. Anyway, the wedge product is that two-dimensional sort of parallel concept. And as it turns out, del wedge F straight up exactly gives you that exact same formula. So how about that for convenient? It's kind of nice. Now again, some more alternatives. I like to call this thing Green's operator because after all, it is the operator that makes Green's theorem work. So I think that's a really natural little bit of terminology. I call it Green's operator sometimes just for that reason. But I think that's, a little niche. I'm not saying that you're going to hear that a lot, but just so you can understand, something I might say in the future, heads up, I'm going to call it Green's operator. And with that in mind, I went through a phase a few years ago where I was writing it as GRN, and there's a long story as to why I felt that was necessary, and I've kind of abandoned that at this point for, again, long story, a bunch of reasons. But if you look at my old exams, in many cases, you will see GRN, nothing to worry about. It just means curl. That's all it is. It just means this formula. Okay. And then in the book, in at least one place, they use this notation, and I don't care for this notation. I have good reasons to not like this notation. Short version, this notation suggests that there's a cross product you can talk about. I will point out we are in 2 dimensions, and there is no cross product in 2 dimensions, and so that notation is flawed and a little bit of a problem. And it can be, you can kind of wave your hands and make sense out of it, but it's intrinsically fishy. And I will also point out, pointless, right? Because look at all these other notational alternatives that we have, right? And so why do we need another one that's a problem? I don't see the point at all. Okay. All right, so heads up for all these different notational alternatives. Let me pause here real quick for questions. Does anybody have any questions about? We got some examples coming up in just a couple of minutes, but anybody questions about this development? Let me remind you, this is just our first example of this program, this sort of game plan in action. The game plan is identify when you have an accumulating quantity, namely the whole is the sum of the parts. Check. Notice that you can view it as a substance distributed over the interior, like a stuff. Check. Weird, but check. Interpret it as having a density. Yep. And write the quantity as an integral of that density. And that is exactly what we've done here. Okay, yeah. No, the density is literally the curl. Yeah, so let's see, let me highlight. So the circulation density is the curl. And if you want to know how much circulation are we collecting in a given little piece of area, that is curl times area. So it's dense. So think of circulation as being a stuff. Think of curl as being a density, which is stuff per unit size. And so stuff per unit size times size gives me stuff. Is that satisfying? Yeah. Okay. All right, now before I do an example, I do want to close one little loop here, and that is I promised you an interpretation of why some people will call this rote. Why do we call it rote? And by the way, this also addresses the question of I owe y'all an explanation from chapter 3 as to why can I just claim that this formula here called curl allegedly is telling me how much of sort of a rotational element there is in the fluid. So these are really the same question. Right? So I guess I could say one question is the answer to the other question. Why do we call it rot? We call it rot because curl represents how much rotation there is in the fluid. Okay, but again, that begs the question, yeah, but why does curl represent a rotation? And the answer there is, let's see, let me go back to here, and we're going to go a few pages back. Yeah, here it is. Don't forget what circulation is. Right? And there's various different interpretations of circulation. How much is the fluid flowing along the curve being a curve that goes around, in some sense, in a circle. But our punchline on that was circulation suggests how a little leaf, I like to think of a leaf, but some floating object in the fluid, circulation suggests how much that floating object would rotate. Because that's what happens when the fluid, if you have a fluid flowing around something, that's what would make that thing rotate. Right? So circulation definitely represents a certain amount of rotation. A rotation in the fluid. Well, if circulation represents a rotation, circulation density, likewise, is representing how much of that rotation comes from what's happening in any given general vicinity. It's rotation per unit area. And that's, again, I think pretty reasonable to call it rot. Okay. So that's that. Let's do an example. Now, to see this in action in the way that it gets used most often, I'm going to give you a different take on Green's theorem. My kind of favorite take is that we have an accumulating quantity that's an integral of a density. I really like thinking of it that way. I think this is the most the most intuition per unit effort point of view on how to think about Green's theorem. We have an accumulating quantity that's an integral of a density. But in practice, let's just look at the formula. I mean, here's the formula says that if I have a line integral around a boundary, oh, that's right, we have a term for this. If we have a boundary circulation, that's what the left side is. And the right side is a double integral computed over the interior. So the blunt, what do they call it? The prima facie, the direct blunt interpretation of what this theorem says is if you have a circulation integral and you want to compute that circulation integral, you have a computational alternative. Instead of computing that circulation by brute force, you can transform the question and say, hey, how about this? How about I compute this double integral instead? It gives you a computational alternative. So that's what we're going to use it as. And here's our first example. We are going to compute this line integral right here. The curve given. Clockwise oriented unit circle. Like so. And over that curve, I want to compute a line integral of that vector field. And we're just going to compute. Now, there's different ways that we can proceed in this computation. The obvious way to approach computing this is, it's literally a line integral. We can literally parameterize that curve and pull back through the parameterization chapter 5 style, right? And just plug and chug, and you can totally do that. And I think that would be a little bit of a nightmare, frankly. And let's just take a moment to recognize and sort of marvel at how much of a nightmare this would be. Unit circle, how do you parameterize the unit circle? Sines and cosines. X and Y are going to be sines and cosines. Now imagine plugging in sines and cosines into that expression. And so, for example, you would end up with tangent of sine of t. That's weird, right? Now, I'm not saying that you can't compute an integral that has that in it. I'm just saying that's going to be a weird integral. Okay, so let's look at our alternative. Our alternative would be able to say, line integral? Oh, line integral. Green's theorem will compute line integrals. How about we use Green's theorem to look at this a different way, look at it as a double integral, and maybe that double integral will be easier to compute. Does everybody see the idea, sort of the hope? Okay. All right. There's an asterisk. Very important asterisk. You got to be really careful about this. I've seen students step on this landmine many times, and it's a tragedy every time I see it. Anyway, here's the asterisk. Green's theorem does not allow you to compute just any line integral you want. And it says so right here. It says so in the fact that right here you see it says that this only computes boundary line integrals. That's incredibly important. It's got to be a boundary. And I want to remind y'all from last time, I guess, the word boundary going forward is a loaded word. Boundary means oriented a certain way. It does not just mean where the fence is, right? It means and oriented according to a certain convention. So we have to look at this curve down here and ask, is this curve a boundary? And don't answer too quickly. That curve, now again, tempting to say, yeah, it looks like it's the boundary of this disk. No, it's not. It's not oriented the correct way. It's a nasty little detail devil, but it's important, right? This is not a boundary because boundary means, and I'm going to use the sloppy intuition, but boundary means counterclockwise. This is not counterclockwise. How are we doing? Everybody see the problem? Okay, well, okay, fine. So how are we going to deal with this? The workaround is actually no big deal. This this clockwise curve that we have, notice it's actually not that different from the counterclockwise curve, and that counterclockwise curve is literally a boundary. It's straight up, no asterisk. It is the boundary of that disk. This disk D that we were talking about a second ago. The boundary of D is C minus. Right? So I can compute the integral on C minus with Green's theorem. I need to compute the integral over C. So all we got to do is just recognize that we're off by an orientation, and being off by an orientation means that I'm going to get a minus sign. And the integral that I want is just the negative of the integral that is a boundary. Are we good so far? We've dealt with the minus sign. We've dealt with the orientation problem. The orientation problem just gives us a minus. Everybody happy? Okay, well, sweet. We have ourselves a boundary. We invoke Green's theorem. Green's theorem says that this boundary line integral is a double integral of curl. Don't forget to carry through that minus sign, by the way. That minus sign doesn't just disappear. That minus sign keeps a coming, right? But this blue boundary line integral is a double integral of curl, and we've transformed the question into a completely new question now, and fingers crossed that this is convenient. And let's keep in mind we're talking about I keep running out of colors. I'll use yellow. We're talking about this vector field F. Apparently we're going to need to compute the curl of this vector field. Don't forget we have a formula for curl on the previous page. Here it is. Curl is that little formula. Right? dq dx minus dp dy. And you punch that up. ends up being 2. And so not only have we transformed the question from a line integral into a double integral, but we've transformed it into a question which is a double integral that is a super easy double integral. It's the integral of a constant over a garden variety geometric shape, and easy integral and victory. Everybody see what happened there? Yeah. Oh, I'm sorry. Yeah. Questions? Yep.
I guess the best way to know whether you're you just have to draw. I mean, I guess it doesn't really outright do the circle, but if you're just given a shape,
Yep.
if you just need to draw it and make an assumption.
Yeah, geometry and just looking at the picture is hard to beat for realizing whether what you're looking at is going the correct direction or not the correct direction. And the next example is going to be a very even more illustrative of this point. Yeah, absolutely. Yeah, you got to make sure you understand if the question describes a certain geometry, you have to look at the geometry, analyze the geometry as it is, and interpret from the geometry. Yeah, for sure. Okay. All right, so let's see here. A strategic observation that I'll make here. Green's theorem is a way of turning one question into a different question. What we've done here, it turns a line integral problem into a double integral problem. It's a tool. It's not a magic wand. There is no promise that the new integral that you turn it into will necessarily be easier. Now, I chose an example here that made it easier because I'm trying to make a sale, right? I'm trying to persuade y'all that Green's theorem is a good thing. And so I picked an example where it works out great. And this new integral here, of course, is fabulous, way easier than the original question. But again, it's just a new integral, and there's no law that says it's going to have to be easier. So kind of like, think back to single variable calculus, integration by parts. It's a tool, not a wand, right? It turns one integral into a different integral. Doesn't have to necessarily be a better integral. Sometimes it makes it worse. If it makes it worse, don't do that, right? So same thing with Green's theorem, works sometimes, sometimes not. Okay, here's another one. This is a weird one, but I think this is a good kind of weird. So we have a collection of line segments that goes from this point to that point to that point to that point to that point, and altogether it's that segment followed by that segment followed by that segment followed by that segment. And you can see we have here a closed curve. Okay. So, all right, we want to compute that line integral, this vector field. What I like to do on this question is break it up in a different way. And I'm going to view it as this segment plus that segment plus that segment, which is literally the boundary of that little left triangle. That's fabulous that it worked out to be a boundary. We know what to do with boundaries. Green's theorem is going to crush that. And then plus, let's see here. That segment plus that segment plus that segment. And it's tempting to call that purple trio of edges a boundary because it does go all the way around D2, but it's going the wrong way. And this matters. So, okay. Yeah, so fine. So we recognize that the boundary that this relates to, this collection of green edges, same edges, just going the opposite direction, that is a boundary. That trio of green edges is the boundary of that triangle on the right, boundary of D2. Sweet. And it's just that what we want being the purples, is same thing, opposite orientation. So we just acknowledge that with this superscript minus sign. How we doing? Is everybody with me? Okay. So, yeah, take it from there, and this blue line integral is a boundary line integral and therefore a double integral of curl. Green's theorem, like I say, crushes it. Okay, so the green is a boundary line integral and therefore double integral of curl, and again, Green's theorem crushed that one too, except for the fact that that's not really what we want. What we want is the negative of that. And so we just recognize that with these minus signs, and the blue plus purple that we wanted in the first place, well, blue plus purple is just blue minus green. What do you think? Everybody happy with that? All right. Okay, now let's try to figure out, did this help us? I mean, is this any easier than this was in the first place? And I think it is. I think this is easier. And the reason why it's easier is because of how the curl computation works out. And let's see here. Remember, we do have to compute for this vector field. I've got to compute the curl of that vector field, and it's just various partial derivatives. And again, y'all can do the details there, but if you take those partial derivatives, this curl ends up being 9, which is a constant. I love constants, right? And so very nice that the curl is 9. And constants in particular are nice because their integrals are just that constant times areas. And I think you can persuade yourself that these areas are in fact the same. And so we get something minus itself, and we get 0 then as our final answer. How we doing? Everybody happy? Okay. All right. Okay, so these are a couple of computational examples. There's many more computational examples. Y'all are going to have some of the exercises, of course, but it's this kind of thing. And let me show you some other applications of Green's theorem that end up being kind of handy. This first one is very tricky and very clever, and in some cases, when it comes up, is extremely valuable. Yeah, let me start with how it works. By the way, this is a sort of a two-step process, kind of a 1-2 punch of ideas. They're both clever ideas. They're independent, clever ideas. We'll take them one at a time. We'll start with this one, this top line. Really clever idea here. I'm going to start with Green's theorem, which you'll see right there. This is Green's theorem. Boundary circulation is a double integral of curl, right? That's just Green's theorem. But it's Green's theorem applied to this special vector field. I claim that this is a special vector field. Oh, let me leave the... There is something very special about that vector field. This is not a uniquely special vector field, but it is a special vector field. What's special is that its curl is 1. Now, like I say, that's not a unique, there's lots of vector fields where the curl is 1. You can dream some up on your own. Any vector field where the curl is 1 will do just fine for these purposes. I like this one. So why do we care? Why is this useful? Why is it advantageous for the curl to be 1? Well, when the curl is 1, we're literally doing a double integral of 1. We're literally adding up a bunch of little pieces of area. So it computes the area. And that's kind of a surprise already. One little detail to add, but isn't it a surprise that a line integral would compute an area? I think that's weird. Everybody see how that's unexpected? Okay. All right, now, again, this is just kind of the first part of the story. I will end on this first part by noting this notational alternative. We talked about coordinate line integrals either last time or the time before. It's just a notational thing. Just remember that dr, this dr right here, is dx comma dy, and just write out the dot product, and it gives us this. So we have this coordinate line integral alternative, and This is one of the few, I think that's fair. This is one of the few circumstances where the coordinate notation, I think, is even more convenient. Most of the time, that coordinate notation is kind of bulky and clunky. In this case, I think that rolls off the tongue really nicely. Integral x dy. That's pretty compact. It's pretty convenient. So most of the time, this theorem you will see written as integral x dy equals area. All right, now that's the first half. The second half, the second punch of the 1-2 punch, is this little observation right here. And this is just a brute force calculation, plug and chug. Y'all can totally do this yourselves. In fact, I encourage you to do this yourselves. Parameterize the straight line segment L that starts at x1, y1 and goes to x2, y2. Good little exercise in parameterizing curves. Think back to chapter 1. Talk about how to do this in chapter 1. You parameterize that literally. You plug in, you plug and chug. No tricky curves. You just plug and chug. And what you find, very convenient little answer, is that when you're, when you are talking about a straight line segment, this line integral that we're interested in can be computed ultra conveniently. It's just the average value of x on that line segment times the change in y on that line segment. That's it. Simple arithmetic. Look how easy this arithmetic is. It's 4-function arithmetic. Super easy. All right, so the big picture strategy then, putting these together, if you want to compute an area, we're going to compute an area as an integral if that boundary curve is made up out of straight line segments. You can just compute that boundary circulation as a bunch of straight line segments, each one of which using this super easy little formula, and bam, you can compute the area for an example that otherwise might be geometrically really inconvenient. And here's our example right here. And just for fun, again, before we do this the smart way, let's entertain the question of how I would compute this area. Right? Think back to high school geometry. If this was a high school geometry class, how would you compute that area? Well, I guess would you break this up into a bunch of triangles? Right? But here's what stinks, though. If you break this up into a bunch of triangles, they aren't right triangles. Most of them, at least. One, two, three, four, five, six. You have 7 triangles. How do you compute the area of a triangle when it's not a right triangle? Well, I guess you could look at the edge vectors and compute various determinants and stuff like that. But it's going to be kind of inconvenient. Or you could use formulas like Heron's formula from way back when. I don't know if do they still teach Heron's formula? Probably not. Okay, don't worry about it. It's not something we're going to do anything with. But it's not convenient either. So here's the very convenient alternative. And that is to, again, take these one at a time. Let's look at one edge at a time. Start with that first edge. Remember what we got to do, we're going to have to eventually compute the boundary line integral over the whole boundary. But we're doing it one edge at a time, and for each edge we're going to look at x bar times delta y. Again, here we go. So for that first edge, what is x bar? What's the average value of x if x starts at 1 and ends at 12? And the average value of x then would be 6.5. That was easy. Right? And then let's see, now I've got to multiply by delta y. What is delta y? Well, y started at 1. Whoops. Y started at 1 and ends at 6. So delta y is 5. And the integral on this edge then, the integral on that edge is the product x bar times delta y. So it's this times that, which is 65 halves. That was easy. I mean, really easy for that one edge. Is everybody on board? Everybody see how that was easy for that one edge? And just keep going. All right, and let's clean up the mess here. But for that first edge, we got this. And then for the second edge, we would get that. And then for the third edge, we get that. And you just keep going around. There's only 9 edges. Okay, there's several edges. But each one is easy. And then you just add them up to compute the entire thing. You add up all 9 of these, and your total area is 19. And we didn't even have to get our hands dirty. No trig, right? No square roots, nothing weird. Simple arithmetic. Everybody with me? Yes. Yeah. Then this doesn't work. This absolutely doesn't work. Yeah, no, that's a great question. And again, the sticky wicket for Green's theorem. Green's theorem only works for boundaries. Yeah, and boundaries don't have any sort of openings. It wouldn't be a boundary, right? So yeah, absolutely. Yep. Okay. All right. Okay, so a nice little cute application. Let's see another application. This is about flux. And y'all probably remember we talked about flux a long time ago, back in chapter 3. And we, in particular, talked about 3-dimensional flux. And the big idea of flux is you've got a fluid that's flowing. Like, let's say air in this room maybe is flowing that way. And if I have a surface maybe angled in some weird way, and I want to know how much fluid per unit time is flowing through that surface, and accounting for how the surface is oriented or compared to the direction. How do you do that? And we wrote down a little calculation, and it ends up using dot products, and we ended up with a formula, and that was called flux. Okay. This is the same thing, just 2-dimensional instead of 3. And I'm going to leave it to y'all to do this computation. It's very doable. It's a shameless rip-off of what we did in chapter 3. So when y'all prove this theorem on your own, what I want to encourage you to do, go back to chapter 3, see what we did for 3-dimensional fluids, and just kind of do the 2-dimensional equivalent. The argument will totally translate. It's practically identical. Right? It's 2-dimensional instead of 3. And what you end up with is that the flux depends on the vector field describing the flow. And it depends on the length of the edge, the little straight line segment that we're looking for, how much fluid is flowing over that edge. And it depends on how that edge is oriented. And so again, we need to have a unit normal vector like so, and notice this result is in fact even pretty familiar. In 3 dimensions, it was f dot n times area. Here we get f dot n times length. Very analogous punchline. So again, I think this is a healthy exercise. Give that a try. As always, if you get stuck, not sure how to proceed, come talk to me. I'll be very happy to walk you through it. Okay, so this is what we're going to start with. This only works through a straight line segment. Let's ask the harder question now. What if I have not only something that isn't straight, but an entire boundary curve of some region? How would we compute boundary flux through that entire boundary? That's what we're going to try to address now. Okay. Now, the first step on this is pretty straightforward. We're going to take this boundary curve and we're going to chop it up into little pieces. And we're going to add up over each little piece. No big deal. Right? If I look at the flux over each of these little pieces and add up over all those pieces, I will get the whole boundary flux. Is that believable? Everybody happy with that? Okay. All right. All right, well, on a little piece, if I'm looking at a little piece of line segment like this, well, it is approximately straight. It's approximately a straight line, so we can use this formula. F dot n times the length of that piece. So it's easy to write this as this. So far, so good. Everybody with me? Okay. All right, and here's where we have to get clever. We don't know what to do with this integral. We've never seen an integral like this before. In particular, we don't know what to do about having normal vector times ds. We've seen tangent vector times ds. We've never seen normal vector times ds. So, what are we going to do about this? Here's the clever idea. Gosh, I wish I thought of this. Somebody showed this to me when I was about y'all's age. It's a very, very clever idea. It comes from looking at these two vectors, f and n. We got some vector field. We're dotting with the normal vector. And let's just look at what happens when I take this entire picture and rotate everything counterclockwise 90 degrees and see what we get. Well, if I take the field vector p comma q, I know how to rotate something 90 degrees counterclockwise when I know the coordinates. I get minus q comma p. Now again, that's a linear algebra thing. You can write down the rotation matrix. Make sure you know how to write down a 90 degrees counterclockwise rotation matrix. Columns are the images of the standard basis vectors, right? Write that down, multiply by p comma q. You get minus q comma p. Make sure you can do that. Again, come talk to me if you can't. If you have trouble, come talk to me. And then the really clever idea, what happens when you take this outward normal vector? By the way, that's the convention. When you're talking about flux, the orientation convention is always outward. Arbitrary but standard. That's the way it is. It's just the way it is. It's somebody made this decision hundreds of years ago, and we're stuck with it for good or for bad. I think it's fine. But anyway, that's the convention. When you take that outward normal and you rotate 90 degrees counterclockwise, you get a tangent vector. But furthermore, geometric appeal. Let's see if I can get this down where I can reach it. From outward, if you rotate 90 degrees counterclockwise, you'll be going tangent to the curve in the direction where the region is on your left. So this will always turn the standard outward normal always rotates counterclockwise to the standard counterclockwise tangent vector. So n always rotates to t, our unit tangent vector. And so now all together then, let's look at what happened. We were interested in this dot product, f dot n. I was interested in the dot product of these two vectors. I took those two vectors, I rotated them both 90 degrees counterclockwise, and that doesn't change the dot product at all. The magnitudes don't change, the angle between them doesn't change. Remember, dot product is the magnitude of the one times the magnitude of the other times the cosine of the angle in between. The magnitudes and angles didn't change. And so this purple dot product is equal to this blue dot product. Right? I can replace that purple dot product with the blue dot product. And lo and behold, this problem in ds that we didn't know how to deal with has now turned into TDS, which is dr, which we are experts on how to deal with. Everybody see what happened? It's a super clever trick. Very clever. I did not figure this out on my own. Somebody showed me this. So likewise, don't ask yourself, oh my gosh, I never would have thought of that, right? you get to benefit from the experience of, our mathematical forebears, just like I did. Okay. All right, so it's all over with shouting at this point. I guess let me not go too fast here. I'll try to get this all on. There we go. We have ourselves a line integral, a boundary line integral, no less. Green's theorem does the heavy lifting. Green's theorem turns this into a double integral. We write down the curl. Be careful here. We're taking the curl, not of f. We had to make this little rotation argument. We're not taking the curl of f, we're taking the curl of f perp. And so when we write down the usual formula, it's tempting to sort of memorize character for character, dq dx minus dp dy. It's really the x partial of the second coordinate minus the y partial of the first coordinate, like that. Easy to whoopsie that. And then you distribute the minus sign, and we end up with our integrand being that, which you may recognize, again, flashbacks to chapter 3, that is divergence. Okay, so a lot of sort of details to be thought about, but nice punchline. Flux is a double integral of divergence. As a very handy little computation, if you wanted to compute that flux, again, you could brute force it. You could try to do this directly, and again, I claim that's usually fairly inconvenient. By the way, I'm sorry to have to tell you this, but one of the exercises on the homework will ask you to do one of these computations directly. And it's a special case where it's not so bad, it's doable, and you can do it. And then the second part of the question says, do this instead, isn't that nice? Right? And this is one of these exercises where the purpose is to make sure that you appreciate the nice formula by contrasting it with the alternative. Okay. All right. By the way, this over here is just another notational alternative. Suit yourself. The punchline is you can note that dot products and wedge products relate to each other. Y'all may recall wedge products from chapter 1, section 1.4, very end of section 1.4. Wedge products are kind of a two-dimensional, it's not an analog, but it has some similarities with cross product, kind of loosely. But anyway, A dot B is A wedge B perp, and that allows you to turn this integral into this integral. It's just a different notational choice. Wedge dr. Honestly, I did not see this very much in my physics classes when I was y'all's age. So I don't know how much y'all are going to see this. But it is very compact. I think, just from if you had to pick which of these is the simpler notation, I think you'd have to go with this. But being less common, you may want to just stick with that one up there. Anyway, it's a notational alternative. Okay, let's do an example. Let's compute the flux. And we have a vector field given. And we have the curve given. And how do we compute this? Well, the theorem up here that we just got through proving says that flux is just a double integral of divergence. You don't have to parameterize the curve. You don't have to deal with the normal vector and orientations. You have to recognize that it's oriented correctly outward, right? But you don't have to actually write down that orientation vector, and you can just say, okay, double integral of divergence. And the vector field, it's really easy to compute the divergence. Divergence ends up being -3. So again, this turns into a really easy double integral, and altogether the flux is -3. Works out really nice. Everybody okay? Everybody with me? Okay. All right. And this is a pretty good stopping point. I think we're basically out of time anyway. We'll draw the line right here. Y'all have a good rest of your day. See you on Friday.